There's something mysterious about the universe. Intriguing, fascinating. What's really out there? How did it all come about? Are the stars just like our sun? Perhaps some with planets, and some of those with life, and maybe some of that life like us? We look at stars and theorize. What's going on? We've only a handful of facts, each one paid for with years of observing starlight. But stars send us a lot more than just light. Stars are sources of incredible amounts of energy, and this energy is broadcast throughout the universe as light, radio waves, X and gamma rays, and cosmic particles. And these energies tell us about startling objects in the universe. Quasars that look like large stars but produce more energy than 10,000 billion stars. Pulsars, the collapsed remnants of supernova explosions that sweep beams of energy across space like a lighthouse beacon. Black holes, huge, massive stars that have collapsed to something perhaps 5 miles across, and so dense that even light can't escape their tremendously powerful gravitational fields. The recent discoveries of these bizarre and exciting objects have led to revolutionary new theories about energy, matter, and the origin of the universe. These discoveries may shake the very foundations of science, carrying scientists beyond atomic and nuclear physics. Why all this excitement? It's as if we've discovered a new universe. In fact, in the past few years, we've learned more about some of the things going on out there than in 3,000 years spent gazing at starlight. Up until this century, all astronomy was done by human eyes and telescopes. But the human eye can't see high energy. And even if the human eye could see high energy, the high energy universe is hidden from us by the Earth's blank atmosphere. Light and radio waves pass through the atmosphere fairly easily. But the electromagnetic spectrum covers an extremely broad range of energy waves, including X-rays and gamma rays, which are absorbed by water and other molecules in our atmosphere. We have to get above the atmosphere and use special instruments to conduct high-energy astronomy investigations. And this is exactly what we're doing. NASA is cooperating with leading scientific institutions and industrial firms across the nation and Western Europe in constructing a series of 3 high-energy astronomy observatories, HEAOs. They will be launched in 1977, 78, and 79 to explore the new high-energy universe.
Most of the stars that we see in our universe burn by burning nuclear fuel. There are, however, stars and galaxies in which energy is released in much greater amounts than occurs in our own sun, and the energy release occurs very suddenly. We call these events explosions occurring in stars and galaxies. What causes these explosions? What physical processes go on that produce them? And what is the role of explosions or explosive events in the creation and evolution of the universe is the proper field of study for high-energy astrophysics.
Great breakthroughs in physics come once in a generation. The practical benefits often come a generation later. 50 years ago, we were concerned about atomic physics. Now we have nuclear energy and many other benefits to mankind. Solid-state physics is now giving us miniaturized computers.
We don't know where high-energy astronomy is going to take us. It will enable us to test general relativity in ways which have never been available to us before. It will give us an entirely new look at the universe. We can't afford not to look.
X-ray astronomy really began in 1962 with rocket launches and the discovery of X-ray sources in our galaxy. By 1969, we had detected sources to the far ends of the universe.
Rockets have a very short time above the atmosphere, and we need to be in that position to make X-ray observations. Pinpointing of these sources and their exact location was difficult to ascertain in such a short time. Therefore, NASA decided in 1970 to launch a small astronomy satellite to take a more penetrating look at all the X-ray sources that could be discovered with such a primitive instrument as was available to us at that time. Out of these small satellite observations, Dr. Giacconi and his group of scientists developed this map. It consists now of about 160 sources, most of which are located in our own galaxy.
The study of stellar evolution tells us that the stars spend most of their life quietly burning away their nuclear fuels as if they were giant reactors in which the hydrogen transmutes into helium and then the helium in carbon and so forth. Once all of their nuclear fuels are burned, very dramatic changes occur, particularly in stars which are more massive than our own sun. What happens is that the force of gravity acting on the outer layer of the stars can no longer be balanced by the pressure of the heat inside, and therefore the outer layers collapse, lag behind, and then are explosively ejected, and we have what we call a supernova explosion.
On July 4th, 1054 AD, a spectacular supernova was recorded by American Indians and Chinese astronomers. This supernova produced the Crab Nebula, but it wasn't until 1968 that radio telescopes found a very small blue star pulsing in the center of the Crab Nebula.
At first, the regularity of the pulsations they were observing led them to think that this might be signals from an intelligent civilization trying to communicate with us. It was later decided that these were natural signals produced by a collapsed star, a pulsar, found at the center, the remnant of the supernova explosion. What we think happens in a supernova explosion is that as the nuclear fuel is burned, the outer layer of a star starts collapsing toward the center. If the star is very massive, there is no force that we know of that can prevent it from being crushed to about 10 kilometer size, retaining the same mass.
This is like crushing the Earth into the size of a football field. As it gets smaller, it spins faster, and since the amount of matter is essentially the same as when it was a larger star, its magnetic and gravitational fields are still as great. In fact, they are tremendous compared to its now very compact size. In a neutron star, the collapse stops when the atoms have been crushed together to such an extent that instead of having separate protons and electrons, we have a neutron soup. Now, if a neutron star is in orbit around a normal star, like the pair of stars in Hercules, then as the normal companion loses mass, the gravity from the compressed star captures the matter from its neighbor. As the matter falls into the magnetic poles of the neutron star, it heats up to very high temperatures and shoots out a stream of energy, X and gamma rays, that our satellite observatories will be able to record. But why does it appear to be pulsating? When the magnetic poles are not the axis of rotation, every time the star rotates, the stream of energy is swept through space and appears to us as a pulse.
But in nature, theories of gravitation tell us there can be even more exciting objects. Objects which are so massive that the collapse does not stop at that point and continues. This is a black hole. Black holes may exist in nature in very large numbers. There may be very large masses, small masses. For instance, there could be a very large black hole at the center of our own galaxy, which accretes gas and dust as if it were a cosmic vacuum cleaner.
Oppenheimer predicted as early as 1930 that the end point of stellar evolution had to be a black hole. If the original star is massive enough, when it collapses, everything is crushed under the tremendous gravitational force to some sort of basic superdense form, resembling primeval matter. Its gravity becomes so strong, even light could not escape the neighborhood of this black hole. And if no light or other energy escapes it, we can't see it. We call it a black hole in space. Matter and energy are sucked in, but nothing ever comes out.
In 1972, as we were scanning the sky in search of X-ray sources with the instruments aboard the Uhuru satellite, we noticed a very rapidly flickering star. And by studying its X-ray emitting characteristic, we concluded that we had the best candidate for a possible black hole. That star has become very intensively studied, and it's very well known now by its name, Cygnus X1. One of the fascinating questions in astrophysics is how the tremendous amount of energy we see released from Cygnus X1 is actually produced. Here on Earth, if I took this stone and dropped it, the stone would acquire a certain amount of kinetic energy, and as it drops to the ground, would make a little dent. But that energy, of course, is very small. If I took the same stone and I burned it in a nuclear reactor, then I could get much more energy. If I drop this stone in a black hole, the amount of energy which is acquired is many, many times what I could acquire by burning this as nuclear fuel. And that is the origin of the energy release in Cygnus X1.
But we think we have discovered something outside our own Milky Way galaxy, even more energetic than the black hole. The mysterious quasar.
Quasars are the most violently energetic objects in our amazing universe. If we believe the redshifts, they tell us that the most distant quasars are near the edge of the universe.
Measuring redshifts is a method that astronomers use for determining the speed which a distant object, such as a star or quasar, is traveling. Light is energy waves, and in the visible range, shorter waves are blue and longer ones red. Now, if a source of light were moving toward us, then the light waves would crowd up, get shorter, and the source would look blue. When we look at a quasar, we see it moving away. The waves are stretched, and it appears to shift to the red. This phenomena is called the Doppler shift.
Quasars have been detected with redshifts that correspond to 90% of the speed of light. The quasar 3C279 was observed to flare to more than 10,000 times the brightness of the Milky Way in about 13 days. That means that its size is something like 13 light days compared to 100,000 light years for the Milky Way. Nuclear energy is no explanation for that kind of phenomenon. We believe some form of gravitational collapse, perhaps a supermassive black hole, 100 million suns collapsed to a black hole, may be involved. We don't know whether quasars are some link in the normal evolution of galaxies or something totally apart.
As a result of these astounding findings, the National Academy of Sciences put more emphasis and higher priority on additional studies and observations. NASA decided to initiate a new program of larger, more sophisticated satellites, the HEAO program. Equipment for these 3 HEAO missions is now being assembled across the country by men and women in scientific, educational, and government installations. This equipment consists of large and sensitive X-ray, gamma ray, and cosmic ray detectors.
What we plan to do with the HEAOs is launch 3 different observatories in 1977, 1978, and 1979. They'll be launched by rockets from the Kennedy Space Center in Florida. Each observatory will weigh 7,000 pounds, and there'll be 2 major sections of each observatory. There'll be the experiment module and a spacecraft module. When they're flying, they'll actually be joined together.
The spacecraft module will provide all the necessary housekeeping functions for the experiments, keeping them at the right temperature, providing them with electricity, collecting the data that the experiments observe on orbit, and then taking that data and radioing it to the ground for the waiting scientists and ultimately the world. HEAO-A will rotate slowly, so that over a 6-month period of time, we will scan the entire cosmos, marking a map of all the X-ray objects that can be observed. When that map from HEAO-A is developed, HEAO-B will then be launched. The HEAO-B X-ray telescope will actually point at various objects that have been identified on HEAO-A, so they may be studied in great detail. By correlating these X-ray observations with those of optical astronomers, we will better understand these fascinating objects and events in our universe.
HEAO-C will be launched in 1979 and be quite similar to HEAO-A. It, however, will carry a cosmic and gamma ray payload and again do an all-sky survey.
In the last few years, we have begun to increasingly realize the importance of explosive events occurring in pulsars, black holes, and quasars in the birth and death of stars and galactic systems and in their evolution. Whenever these conditions occur in cosmic objects, high-energy photons and high-energy particles are produced, and this can best be detected with high-energy astronomy instrumentation. Therefore, high-energy astronomy has a particular role to play in the study of explosive events in the universe as a whole.
What we hope to achieve, the National Observatory facility that will help us understand man's role in the universe and the sources of the energies and their utilization.
We barely understand our universe. Once thought a place of quiet majesty, now is known to be a bursting hotbed of forces and energies more violent than we ever dreamed. With HEAO, we are opening a new window to see this new universe face to face, to learn more of its secrets and make them our own.